For FRQ3, we are given a sphere, a stopwatch, and a meter stick, and are asked to take measurements to create a graph that can be used to determine the acceleration due to gravity. And for part A, I need to describe a procedure for collecting data that can be graphed to determine the acceleration due to gravity. And we need to reduce the experimental uncertainty. So, in order to find acceleration is equal to velocity over time, while velocity is equal to displacement over time. And since velocity just is recorded in meters over seconds, so the displacement should be meters while the time should be seconds. So I should try to take the data in meters and using seconds. So the first step is we're going to use the ruler, stopwatch, and meter stick and drop the sphere. We're going to use the sphere, and then we're going to drop the sphere at a certain height and record the amount of time it takes for it to reach the ground, which will be our displacement and time. So we'll do multiple trials at that certain height, so we can find the average and reduce the uncertainty. For step 2, we're going to do this at multiple different heights and have multiple trials at those different heights, so we could reduce the uncertainty even more. And step 3, we have our data, and we're going to use that data and graph it on a velocity over time graph to find acceleration, because the acceleration is equal to the slope of a velocity over time graph. And we can find a velocity by just dividing our distance over time. And we can, for step 4, graph the velocity over time. And for step 5, we will just find the slope of this graph, and it should equal to acceleration, which is gravity, and it should be around 9.8. For part B, we are asked to describe how the data collected in part A would be graphed and how that graph would be analyzed to determine the acceleration due to gravity. So the data collected in part A should be displacement and time. So we can graph a displacement over time graph, and we can find the slope of that, which will equal to velocity. Or we can just divide the displacement over time, and that will equal velocity, and just graph the velocity over the time and find the slope of that. And that should equal to acceleration, and the acceleration should be meters over seconds squared, because velocity is equal to meters over seconds, and if you divide by seconds, it should equal to meters over seconds squared. For part C, we are given data from a student, collected from a group of students that are given a cart on an inclined track. And so the data we are given is velocity in meters over seconds and time over seconds. And we are given a velocity of 1, 1.7, 3, 3.7, and 5. And we are given the time 0.1, 0.3, 0.5, 0.7, and 0.9. And we are also given the equation v equal to g sine theta t. So for part C, is told that the horizontal axis is time, and since we are trying to find velocity, it would just mean that the vertical axis, since we are trying to find acceleration, it means the vertical axis should be equal to velocity. And this is seconds, this is meters over seconds, because acceleration is velocity over time. And we are also asked to solve this on the equation we are given. So and we are trying to find the angle of the track. Since data is equal to angle of track, we can just divide both sides by gravity and time. So which will equal to v divided by gt, and do data is equal to sine inverse sine over v over gt. And that means data is equal to angle of the track. And for 2i, we are asked to plot the data points that are given by the students. So since our range is for vertical axis since we're trying to find acceleration, it would mean our vertical axis is equal to velocity, which is meters over seconds, while our x-axis is time, which is seconds. And our range for time is 0.1 to 0.9 seconds. And our range for the y-axis is around 1 to 5. And we need graph the points. So at a velocity of 1, our time is around 0.1. At a velocity of 1.7, our time is 0.3. At a velocity of 3, our time is 0.5. At a velocity of 3.7, our time is 0.7. And at a velocity of 5, our time is 0.9. And we are also asked to draw a best fit line. So it should look like around like this. And the line of best fit is equal to acceleration. And for part D, we were asked to calculate the experimental value for data using the best fit line I drew in part 1 of C, which is this. So since the formula is equal to data equal to g sine, or data over t, or velocity equal to g sine data over t, and since we can just do sine data is equal to velocity over gt, since we divided it, and we know gravity is 9.8, and we need to find velocity and time. We can find the slope at a point in a graph. So we can see these 2 points, we can use these 2 points and find the slope, and we can plug it in and find data. So the slope is equal to 5 minus 1 over, 5 minus 3.7 and 1 over 1 minus 0.7, which should equal to 1.3 over 0.3. And I'm just gonna divide that using a calculator. And this should equal to around 4.3. And since this was meters, over seconds and this is seconds, this should be equal to meters over seconds squared. Afterwards, we just plug it into the graph, or equation. So sine theta equal to and then we find inverse sine. And that would equal to theta would equal to around 26 degrees. So the angle of the track should equal to around 26 degrees.